Node. A standalone computer in a box. Usually comprised of multiple bus/processors/cores, memory, network interfaces, etc. Nodes are networked together to comprise a supercomputer. CPU, socket, processor, core. This varies, depending upon who you talk to. In the past, a CPU central processing unit was a singular execution component for a computer. Then, multiple CPUs were incorporated into a node. Then, individual CPUs were subdivided into multiple cores, each being a unique execution unit. CPUs with multiple cores are sometimes called sockets, vendor dependent. The result is a node with multiple CPUs, each containing multiple cores. The nomenclature is confused at times. Wonder why? Task. A logically discrete section of computational work. A task is typically a program or program-like set of instructions that is executed by a processor. A parallel program consists of multiple tasks running on multiple processors. Pipelining. Breaking a task into steps performed by different processor units, with input streaming through, much like an assembly line, a type of parallel computing. Shared memory. From a strictly hardware point of view, describes a computer architecture, where all processors have direct, usually bus-based access to common physical memory. In a programming sense, it describes a model where parallel tasks all have the same picture of memory and can directly address and access the same logical memory locations regardless of where the physical memory actually exists. Symmetric multiprocessor (SMP) point hardware architecture where multiple processors share a single address space and access to all resources, shared memory computing. Distributed memory, in hardware, refers to network-based memory access for physical memory that is not common. As a programming model, tasks can only logically see local machine memory and must use communications to access memory on other machines, where other tasks are executing. Communications. Parallel tasks typically need to exchange data. There are several ways this can be accomplished, such as through a shared memory bus or over a network. However, the actual event of data exchange is commonly referred to as communications regardless of the method employed. Synchronization. The coordination of parallel tasks in real time, very often associated with communications. Often implemented by establishing a synchronization point within an application, where a task may not proceed further until another task reaches the same or logically equivalent point. Synchronization usually involves waiting by at least one task, and can therefore cause a parallel application's wall clock execution time to increase. Granularity. In parallel computing, granularity is a qualitative measure of the ratio of computation to communication. As following one course, relatively large amounts of computational work are done between communication events. 2 fine, relatively small amounts of computational work are done between communication events. Observed speedup. Observed speedup of a code which has been parallelized, defined as wall clock time of serial execution divided by wall clock time of parallel execution. One of the simplest and most widely used indicators for a parallel program's performance. Parallel overhead. The amount of time required to coordinate parallel tasks, as opposed to doing useful work. Parallel overhead can include factors such as 1 task startup time, 2 synchronizations, 3 data communications, 4 software overhead imposed by parallel languages, libraries, operating system, etc. 5 task termination time. Massively parallel refers to the hardware that comprises a given parallel system having many processors. The meaning of many keeps increasing, but currently, the largest parallel computers can be comprised of processors numbering in the hundreds of thousands. Embarrassingly parallel. Solving many similar, but independent tasks simultaneously, little to no need for coordination between the tasks. Scalability. Refers to a parallel system's hardware and/or software ability to demonstrate a proportionate increase in parallel speedup with the addition of more resources. Factors that contribute to scalability include 1 hardware, particularly memory bandwidths and network communication properties. 2 application algorithm. 3 parallel overhead related. 4 characteristics of your specific application. General characteristics. 1 shared memory. Parallel computers vary widely, but generally have in common the ability for all processors to access all memory as global address space. 2 multiple processors can operate independently but share the same memory resources. 3 changes in a memory location affected by one processor are visible to all other processors. 4 historically, shared memory machines have been classified as UMA and NUMA, based upon memory access times. Uniform memory access UMA. 1 most commonly represented today by symmetric multiprocessor (SMP) machines. 2 identical processors. 3 equal access and access times to memory. 4 sometimes called CC UMA, cache coherent UMA. Cache coherent means, if one processor updates a location in shared memory, all the other processors know about the update. Cache coherency is accomplished at the hardware level. Non-uniform memory access NUMA. 1 often made by physically linking 2 or more SMPs. 1 SMP can directly access memory of another SMP. 3 not all processors have equal access time to all memories. 4 memory access across link is slower. 5 if cache coherency is maintained, then may also be called CC NUMA, cache coherent NUMA. Advantages. 1 global address space provides a user-friendly programming perspective to memory. 2 data sharing between tasks is both fast and uniform due to the proximity of memory to CPUs. Distributed memory. General characteristics. 1 like shared memory systems, distributed memory systems vary widely but share a common characteristic. Distributed memory systems require a communication network to connect inter-processor memory. 2 processors have their own local memory. Memory addresses in one processor do not map to another processor, so there is no concept of global address space across all processors. 3 because each processor has its own local memory, it operates independently. Changes it makes to its local memory have no effect on the memory of other processors. Hence, the concept of cache coherency does not apply. For when a processor needs access to data in another processor, it is usually the task of the programmer to explicitly define how and when data is communicated. Synchronization between tasks is likewise the programmer's responsibility. 5 the network fabric used for data transfer varies widely, though it can be as simple as Ethernet. Advantages. 1 memory is scalable with the number of processors. Increase the number of processors and the size of memory increases proportionately. 2 each processor can rapidly access its own memory without interference and without the overhead incurred with trying to maintain global cache coherency. 3 cost effectiveness can use commodity, off-the-shelf processors and networking. Disadvantages. 1 the programmer is responsible for many of the details associated with data communication between processors. 2 it may be difficult to map existing data structures, based on global memory, to this memory organization. 3 non-uniform memory access times. Data residing on a remote node takes longer to access than node local data. General characteristics. 1 the largest and fastest computers in the world today employ both shared and distributed memory architectures. 2 the shared memory component can be a shared memory machine and/or graphics processing unit CPU. 3 the distributed memory component is the networking of multiple shared memory/CPU machines, which know only about their own memory, not the memory on another machine. Therefore, network communications are required to move data from one machine to another. 4 current trends seem to indicate that this type of memory architecture will continue to prevail and increase at the high end of computing for the foreseeable future. Advantages and disadvantages. 1 whatever is common to both shared and distributed memory architectures. 2 increased scalability is an important advantage. 3 increased programmer complexity is an important disadvantage.